These notes are over the intermediate value theorem. So intermediate value theorem, or from here on out, I'm just going to refer to it as IVT, says that a continuous function on an interval cannot skip values. If we were using a if-then statement to describe this, it would be read as if a function y equals f of x is continuous on a closed interval a, b, and f of a is not equal to f of b, then f of x takes on every value between f of a and f of b on that interval. So pretty much if the function is continuous on a closed interval, and when you plug in the endpoint values of that interval into the function and they are not equal, then we can say there exists some value on that interval. So looking at this graphically, the first one says a continuous function on an interval cannot skip values. So if we were to show this graphically, what we're ultimately showing is that there can exist a value c between a and b, and there can exist a value f of c between f of b and f of a. So if I was to draw this out, I have a and b on my x-axis. I have f of b and f of a. Okay. If I was to draw these points as dotted lines to see where they connect, what I would end up doing is I would be creating a small interval in which any value could exist within that interval. So for a and f of a, I have a point here, and for b of f of b, I have a point here. Now I know, because of this theorem, that there is going to exist a value c between a and b, so I'm going to write c there, which means there's also going to exist a value f of c. And what I'm going to do is I'm going to call this line y equals k. And then I see the next point here. So I know I have some function that is going to go through each of these points, and let's call this function f of x. And everywhere that I'm going to shade is going to be where a possible value can exist on that function. Okay. IVT also can help us find zeros of a continuous function on the interval. So recall, zeros are places where we cross the x-axis. So in other words, we can say f of a is negative or less than 0. And if that is true, then we know there exists a 0 between f of a and f of b. So f of a is negative, f of b is greater than 0. Okay. We're going to do the same thing. I'm going to draw my dotted lines for each of these values to see where they cross. Okay, a and f of a is down here. B and f of b is up here. I know that there's going to exist some value c that is going to be between a and b, where f of c is going to be a 0 value. So that's going to be my third point that is going to be on my function. So I know I have some function, and let me draw that a little better, f of x. And I don't know what the function looks like. I'm just going to connect those values just for the sake of the diagram. Okay. And then same as before, any values in the center of this could be all the possible values that could exist between a and b. Okay, so now let's look at an example. It says, does IVT apply on a specific interval for the piecewise function shown below? Be sure to explain completely. Part A says, is there a value x equals c on the interval -2 to 5 such that f of c is equal to 1? So I'm going to go -2, and I'm going to go 5, and that means I'm looking at everything in between that interval. And then I'm going to find where f of c is equal to 1. So if I look right here at the y value 1s, I notice that I do have a point where it crosses my function right here. So that means there does exist a c on that interval. So I would say, yes, there exists c on -2, 5. This is just a fancy symbol for there exists. Part B says, does IVT guarantee a value of c on the interval -2 to 5 such that f of c is equal to 1? Okay. So now we're looking back at this interval, and we're not just saying, does x equals c exist? We're saying, can we use IVT to guarantee this? Well, remember, for IVT, we have to have a continuous function on that interval. But when we're looking at the interval starting at -2, I could trace this function, and then I have a jump from here to here until I continue the function, which tells me that our function f of x is not continuous. So I would say, no, IVT doesn't guarantee c on -2, 5 since f of x is not continuous. Okay, next example says, is there a value x equals c on the interval 1, 6 such that g of c is equal to 3? So here's 1 and here's 6. So I'm only looking at this interval here. And then I'm looking at y equals 3 for g of c equals 3. So that's right here. Okay, so notice in my shaded region, when I draw the line y is equal to 3, I am not crossing any point of my function. So I would say, no, there doesn't exist a c on 1, 6 such that g of c is equal to 3. Okay, so no, there doesn't exist a c on 1, 6 such that g of c is equal to 3. Okay. Now we're looking at the same problem, and it's saying, well, can we use IVT to guarantee this? Well, since we said that g of c equals to 3, that pink line that I drew never crosses anywhere on that function, it's not going to matter that it's continuous within that interval. Because if we don't have a value crossing the function, then we can't use IVT to guarantee a value of c exists. So we're going to say, no, IVT doesn't guarantee c on 1, 6 such that g of c equals 3 since the value never occurs. So ultimately, what we just discovered is that we need 3 conditions in order to apply IVT. The first is that f is continuous on the closed interval a to b. F of a is not equal to f of b, and we'll see that later on in the examples. and that f of c has to be between f of a and f of b. So looking at the next example, it says apply IVT if possible on 0, 5 so that f of c is equal to 1 for the function f of x is equal to x squared plus x minus 1. So going through each of the conditions, the first condition is saying, is f of x continuous? Well, since f of x is a polynomial, and polynomials are continuous everywhere, f of x is continuous. So this brings us back to a previous notes where we were talking about continuity and all the different aspects of continuity, and polynomials were one of those where we know that they're continuous everywhere. Our second condition is to see if f of a is not equal to f of b. Well, here's our a and here is our b based off of our interval. So I would plug in f of 0 and I would get -1, and f of 5 and I would get 5 squared plus 5 minus 1, which is 29. So this implies that f of 0 is not equal to f of 5. Okay, so that condition is met. Lastly, I have to look at this part where it says f of c is equal to 1. Well, and then I have to check, is 1 between -1 and 29? And if the answer is yes, then I can use IVT. So I would say that by IVT, there exists c such that f of c equals 1 on 0, 5, since 1 is between -1 and 29. Okay. Now I'll do the same thing for this example. I have to do each of the 3 conditions. So the first one is continuous, and just like example 3, this one is also a polynomial, x cubed. So we would say, well, yes, polynomials are continuous everywhere. So when we're actually writing this out, of course, we would write that same sentence we did in example 3. But for the sake of time, I'm just going to say same as example number 3. Please, please, please do not write that in your notes. Write out the full sentence. Okay, the next part is to prove that f of a is not equal to f of b. Well, here is my a and my b. So I have f of 0 is equal to -1. F of 1 is equal to 1 plus 2 minus 1, which is 2. So that means f of 0 is not equal to f of 1. And then I have to check if it has a 0, which what I'm checking is f of c is equal to 0 for some value c. Okay. And since 0 is between -1 and 2, I know I can use IVT. So I would say by IVT, there exists c such that f of c is equal to 0 on 0, 1, since 0 is between -1 and 2. Okay, next example says a car travels on a straight track during the time interval of t between 0 and 60 seconds. The car's velocity v measured in feet per second is continuous. The table below shows selected values of the function. For part A, it says for t in the interval 0 to 60, must there be a time t where v of t is equal to -5? Justify your answer. So our first step is to always see if it's continuous. Where in the problem, it does say that v of t is continuous, so that's enough for us to just write this line. Next, we have to prove if f of a is not equal to f of b. But notice when they give us the problem, they give us an open interval. So what I would do is I would go back to the table and I would say, okay, if -5 was to exist, where on the table would that fit in? And that would be between t is equal to 35 and t is equal to 50, because -5 would fit right in between there. So I'm going to plug in f of 35, and we know that's -10, and f of 50, which is 0. And we're trying to see if -5 would be between those values, which we know it is. So for our third condition, we would say by IVT, there exists t such that v of t equals -5 on 35 to 50. And let me make sure I make those closed intervals. Since -10 is less than -5, which is less than 0. Okay, next example. Number 6 says let g of x equal a continuous function. Selected values of y is equal to g of x are given on the table below. For which value of k will the equation g of x is equal to 3/4 have at least two solutions on the closed interval? So I am going to look at only these values here. And what I'm going to do is I'm going to plot those values. So I have 3, 4, so let's just label that here, 3, 4. And then I have 5, 5. And then somewhere here I have the equation y is equal to 3/4. Okay. Well, in order for a function to have two solutions on this, I know that my function is going to have to go through this y is equal to 3/4 at least 2 times. So in order to do that, I need some value below 3/4. So this tells me that k is going to be less than 3/4. Then I go through all my problems. Well, this is greater than 3/4. 3/4 cannot be less than 3/4. And 3/2 is the same as 1.5, so that's greater than 3/4. So the only possible answer would be 9/16. Okay, number 7 says for the function f of x, find f of 5 and f of 10. Does IVT guarantee a y value k on the interval such that f of k is between these two values? So first, what we're going to have to do is plug in f of 5 and f of 10. Okay, so f of 5 means we're going to be using this top equation in the interval because that's the only one equal to 5. So I have x minus 3 squared, plugging in 5, that's 5 minus 3 squared, which is 2 squared, which is 4. And then f of 10, I would be plugging in the other one here. And notice that no matter on that interval, f of whatever is going to be 6. So I know f of 10 is equal to 6. Well, since f of 5 is not equal to f of 10, we know that that criteria is met. Okay. The next thing we have to look at is if this is a continuous function or not. So in order to see if it's a continuous function, we would have to look at the limit on both sides, okay? Or in other words, we could see if the limit as x approaches 5 from the right of f of x is equal to f of 5, okay? Well, f of 5 is 4, okay? As x approaches 5 from the right, that would be 6. Well, 6 is not equal to 4, so then this is not equal to each other. Okay, so this proves that it's not continuous. And we know if something's not continuous, then we cannot use IVT. So we would say, since f of x is not continuous on the interval 5, 10, at x equals 5, this implies that IVT doesn't guarantee a value k such that f of 5 is less than f of k less than f of 10. And then our last example here, it says the function f and g are continuous for all real numbers, so that's important to know. The table below gives values of the functions at selected values x. The function h is given as h of x is equal to g of f of x plus 2. Explain why there must be a value w for w between 1 and 6 such that h of w is equal to 0. Well, for IVT, we know our function has to be continuous. So looking back at the properties of continuity, we know that since f and g are continuous, this implies that the composition is continuous, which implies h of x is continuous since it has a composition of g of f of x. Okay. The second part is we would be plugging in h of 1 and then h of 6. Well, h of 1 is equal to g f of 1 plus 2. F of 1, looking at the table, is 2, so this is g of 2 plus 2. G of 2 is negative 12, so plus 2, that gives us negative 10. Then we plug in h of 6, and remember, we're trying to see if these two values are not equal. So that's g of f of 6 plus 2. F of 6 is 8, so this is g of 8 plus 2. G of 8 is 28, so 28 plus 2, which gives us 30. So this proves that h of 1 is not equal to h of 6. So the next thing we're seeing is there a 0 value? Because it says h of w equals 0. Is 0 going to be between negative 10 and 30? And since it is, we can say by IVT, there exists w such that h of w is equal to 0 since negative 10 is less than 0 less than 30 on the interval 1, 6.